Welcome! Today we begin Unit 6, Quadratic Functions, and with this video we take a look at problem solving. We are in section 1.7 of the book, and we will cover objectives 1, 3, and 4. Let's get to it, problem solving. In problem solving, we turn verbal descriptions into mathematical expressions. There are real problems, and so what do we do with a real problem? We need to give it some kind of a verbal description. But then once it has a verbal description, in order to work with it, we need to express it in the language of mathematics. And then it becomes a mathematical problem. And once it's a mathematical problem, then I can go about solving it mathematically. And throughout this whole process, I check my work and see that I'm doing it right, that I'm being consistent. And hopefully, if I've modeled the problem well with mathematics, then I might be able to solve the real problem. Look at this. This says the average speed of an object equals the distance traveled divided by the time required. That's a statement that is in English language. But how do I express that in the language of mathematics? The average speed of an object equals the distance traveled divided by the time required. There are three objects, so we need three names for those things: R, D, and T. Let's read that again. The average speed of an object, R, equals the distance traveled, d, divided by the time required. And then I'll say a little thing about what each of those variables means, where r is the average speed, that is r for rate, d is the distance, and t is time. So this is how we might take a statement in words and turn it into a mathematical statement. Let x be a number. How would you write these things? Take a second, try your best, and then start the video again when you want to check your work. Alright, let's take a look. The number 5 times as large as x. How about 5x? The number 3 less than x? X minus 3. The number that is a third as large as x. Either 1/3 x, or you could write x over 3. The number that exceeds twice x by 1. So I form twice x, that's 2 times x, the number that exceeds twice x by 1. So it's 1 more than that. Last one, this is tough. The number that, when added to x, gives 8. You might even have to do a little bit of algebra for this. So something, there's my question mark, the number that, when added to x, gives 8. Oh, so that something I'm looking for is really 8 minus x. So that's the expression that we're looking for, 8 minus x. Let's try some real problems, some mixture problems. This is a classic form of problem you see a lot, mixture problems. Consider this setup. You have a lot of coffee, and one kind of coffee is B-grade Columbia, and it sells for $5 per pound. Now, a little higher grade is the A-grade Arabica coffee, and that sells for $10 per pound. But you want to mix these two together somehow to get a mid-grade. You want a coffee that costs $7 per pound. So how much of the $5 coffee and how much of the $10 coffee should you mix together in order to get something that is exactly $7 per pound? Okay, that's the idea in general. Here is the verbal description. Here are the words. The manager of a Starbucks store decides to experiment with a new blend of coffee. She will mix some B-grade Colombian coffee that sells for $5 per pound with some A-grade Arabica coffee that sells for $10 per pound to get 100 pounds of the new blend. The selling price of the new blend is to be $7 per pound, and there is to be no difference in revenue between selling the new blend and selling the other types separately. How many pounds of the B-grade Colombian coffee and how many pounds of the A-grade Arabica coffee are required? Now, the first thing I want to do is define some variables. Look at the question. How many pounds of the B-grade Colombian coffee and how many pounds of the A-grade Arabica coffees are required? So, two different things I'm looking for. One of them is how many pounds of the B-grade Colombian coffee. Let's call that C. That's the number of pounds that's required. Now, there's going to be 100 pounds in total. So I don't need to make a new variable for the number of pounds of A grade Arabica coffee. Since there's 100 pounds total, and I have C pounds of the B grade stuff, I know that the grade A Arabica coffee has 100 minus C pounds of that. Do you see that? And that way, my C plus 100 minus C equals 100. All right, let's look at this mathematically. The revenue from the B grade plus the revenue from A grade should equal the revenue from the blend. That is, how much money you make if you were just selling the B grade. How much money would you make if you were just selling the A? And then how much money you make from selling the blend. Those are going to be, the sum of the first two equals the third. Well, the revenue from the B grade is, well, let's see, it's $5 per pound, and I'm selling C pounds of that. That was the variable that we just created. Then the A grade coffee, I'm selling it for $10 per pound, and I have 100 minus C pounds. So I will multiply those together to get the total amount of money. And then finally, from the blend, it's $7 per pound times 100 pounds. I'm going to multiply those together to see how much money I get. So we find that multiplying 5 times C is 5C. Multiplying 10 times 100 minus C is 1000 minus 10C, and that equals 700. And now, it really is just a math problem that we can solve. Let's combine the C's together and put the constants on the right. So I end up with negative 5C equals negative 300. Divide both sides by negative 5, and you get 60. So the answer is C equals 60. I have 60 pounds of the B grade Colombian. And then the A grade, let's see, 100 minus C, is 40. I'll have 40 pounds of the grade A Arabica. There, we've solved the problem. So I know I need 60 pounds and 40 pounds in my blend. Let's do another blending problem. How many gallons of oil should be added to 1 gallon of gasoline to make a mixture that is 40% oil? Now, a good first guess would be 0.4 gallons of oil. Maybe I need 0.4 gallons of oil because 0.4 is really the same thing as 40%. So I have 1 gallon of gasoline, maybe I need 0.4 gallons of oil. But that's wrong. Why is that wrong? Well, it's wrong because I'm forgetting that when I add oil, that increases the total amount of the mixture. The oil is just 0.4 gallons, but the total mixture now is going to be 1 plus the 0.4, 1.4. So how do I figure out the percentage that 0.4 is out of 1.4? I simply make a fraction. I do 0.4 divided by 1.4, I get my number, 0.286. And to turn that into a percent, I move the decimal place 2 places to the right. I multiply by 100. So if I only added 0.4 gallons of oil, I'd end up with a mixture that's only 28.6% oil. Okay, so how do I actually solve the problem? The correct way is, let's assign a variable. Let G be the number of gallons of oil that are needed. G divided by 1 plus G has to equal 0.4. That's my 40% that I'm thinking about right there. And I have the oil divided by the total mixture. So the amount of oil that I have divided by the total mixture has to be the 40% right there. So we get, by multiplying both sides by 1 plus G, we find that G equals 0.4 times the quantity, 1 plus G. So I can distribute the 0.4, G equals 0.4 plus 0.4G, and then what? Well, maybe I'll subtract 0.4G from both sides, and if I do that, I'll end up with 0.6G equals 0.4. Maybe to make my arithmetic a little bit easier, I'll multiply both sides by 10. I can do that, and it doesn't change the problem. So 6G equals 4, and divide both sides by 6. G equals 4/6, which is 2/3. which is approximately 0.66. So there's my solution. G equals 2/3 gallons. If I put 2/3 of a gallon of oil on top of the 1 gallon of gasoline that's already there, I'll end up with a mixture that is 40% oil. Rate problems. Okay, rate problems is another big classic category of problems. Let's take a look at this one. This is a good one. Tanya leaves your house running at 8 miles per hour. 2 hours later, you leave in your car traveling at 40 miles per hour, and you soon catch up with Tanya. How long did it take you to catch up with Tanya? Right? Do you see the situation? She leaves, and then at some moment in time, that's when we start the clock, that's when you start in your car. But while you're driving in your car, she's still running. So she is going to make some distance up by the time you actually meet up with her in the car. So what is that time? How much time will it actually take from when you start your car until you catch up with Tanya? So tell you what, pause the video, reread the question if you need to, look at the diagram, think about it for a little bit, and I have given you some hints there. I'll not explain what that is, but maybe think about this for a little bit and see what you can come up with. All right, take a few minutes right now, see what you can do. All right, so I will say the biggest, most important thing is this equation. Distance equals rate times time. Whenever we have motion, this always comes up. Distance equals rate times time. So let's say that t is the time that it takes for the car to catch up with Tanya. That was what was drawn in the diagram here, time t. The distance traveled by the car is 40t. So distance equals rate times time. My rate is 40 miles per hour, and my time is t. T is the variable. That's what I'm trying to figure out. The distance traveled by Tanya is rate 8 times time. So that's the trick here, is that her time is actually 2 plus t, the initial 2 hours that she ran, plus the t hours that it took to catch up. Now, those both represent the same distance, so I can set them equal to each other. 40t equals 16 plus 8t. And then bring all the t's to the left. 32t equals 16. Divided by 32, t equals 1/2. And that is the solution. T equals 1/2 hour. It took half an hour of you driving to catch up with Tanya. Let's take a look at another rate problem. Ellen swims at a rate of 50 meters per minute relative to the water. She is swimming in a river that flows at 20 meters per minute. So just by the way, this means that if she swims with the current, then she's actually going 70 meters per minute. So 50 plus 20 would be 70. If she swims against the current, then how fast would she swim? Actually, 50 minus 20 would be 30 meters per minute. So she swims at a rate of 50 meters per minute, but that can be affected by the current, the speed of the current. Okay, she swims with the current for 30 minutes, and then turns around and swims back to her starting point. How long does it take her to return? I encourage you, if you'd like, pause the video and think about this for a few minutes. Start it up again when you are ready to move on. Let's move on. Going out. When she leaves and swims with the current, recall her distance equals rate times time, and the same thing is true coming back. Distance equals rate times time. The trick is the distance in both cases is exactly the same. She starts, she swims a certain distance, and then turns around and comes back. But the rates and the times will be different. In the first case, she travels at 70 meters per minute. There's the 70 from above. And she does that for 30 minutes, giving her a total of 2,100 meters. Now, what about in the case coming back? Well, we know the 2,100 meters already. That's our distance. And the rate is known. Well, that's the 30. She's traveling at 30 meters per minute because she's going against the current. But the time is now unknown. So I have 2,100 equals 30t. Now we can divide both sides by 30 and figure out what t is. So, how long does it take her to get back? It takes her 70 minutes. So it was 30 minutes to go and 70 minutes to return. Here's a third rate problem that is similar to the second one. We'll continue thinking about Ellen. Ellen swims at a rate of 50 meters per minute relative to the water, so just like before. She swims down, she swims downstream in a river for 30 minutes. It takes her 90 minutes to return. How fast is the river flowing? In this case, I know her times in both directions, but I don't know the rate of speed of the water. So how about this? Let x be the rate of the river current. Do you think you might be able to figure this out? Distance equals rate times time. We use that again and again. Pause the video if you'd like. Think about it for a minute or two. Start up again when you're ready. So again, when she swims out, distance equals rate times time. When she comes back, distance equals rate times time. It's the same distance in both situations, but now let's analyze the rate and the time. When she goes out, her rate is 50 plus x. So that's where the variable shows up. And she swims for 30 minutes. Coming back, now what is her rate? The distance is 50 minus x. And she swims for 90 minutes. So now, maybe we can set those two equal to each other. After all, they do represent the same distance. 50 plus x times 30 equals 50 minus x times 90. Let's distribute. I end up 1500 plus 30x equals 4500 minus 90x. If I put all the x's on the left and all the numbers on the right, I end up with 120x equals 3000. And now divide by 120, and x equals 25. Now what are the units on that? What was that? Oh yeah, x is the rate of the current. So that is meters per minute. And there we go. We've solved our last rate problem. So 1.7, problem solving. You think about how you take words and put them into mathematics and the mathematics that it takes to solve those things. Distance equals rate times time is used again and again and again. And we will see some more of these problems in class. Good luck.